Hello class. This is username, and my project analyzed a wing with and without a winglet to see the effect winglets have on wingtip vortices. Wingtip vortices are what you would expect from the name. A vortex that forms at the wingtip. They form due to the pressure differences a wing experiences at its upper and lower surfaces. Due to the pressure and wing geometry, the air at the lower wing surface flows out and around the wingtip. This motion then causes a vortex that rotates inwards toward the fuselage behind the wing. This phenomenon is not ideal, as the vortex will reduce the overall efficiency of the plane by inducing drag. In addition to reducing efficiency, wingtip vortices can be dangerous. Should a smaller aircraft fly through the wake of a larger aircraft, the vortices could roll the smaller plane so violently that recovery is not possible. With this in mind, I decided to focus on observing how much a winglet can reduce a wingtip vortex. I did this by solving the flow around the same airfoil with and without a winglet and at 4 different angles of attack. The setup of my problem was representative of an aircraft taking off, which is one scenario in which the vortices can be the strongest and have the largest impact on aircraft. Since the wing was modeled through flow similar to that found during takeoff, a relatively low velocity of 50 meters per second was used. This allowed an incompressible, pressure-based solver to be used to solve the Navier-Stokes equations. His turbulence was a variable of interest. The K-omega viscous model was used to take into account these effects and flow separation. As with all other flow problems, continuity was also included. To discretize the governing equations, the simple pressure-velocity coupling scheme was used. The gradient was kept at the default setting of least squares cell-based, while the pressure, momentum, turbulent kinetic energy, and specific dissipation rate were all set to second order. By setting these to second order, the accuracy of the solution increased. The wing and winglet were downloaded from GrabCAD and imported into Workbench's design modeler. Inside the design modeler, the wing was placed in a rectangle representing the domain of the flow. A revolve feature was added to allow for multiple angles of attack to be analyzed. The wing was then subtracted from the domain to allow for a mesh to be created. The mesh for the wing with the winglet was created using the curvature size function and a medium relevance center. 5 inflation layers were also added to help capture flow around the airfoil better. Due to the element limit in the student version, a finer mesh could not be made for the wing with the winglet. The mesh for just the wing was also created with the curvature size function. A fine relevance angle was used and 10 inflation layers were added. Looking at the images shown, the blue faces were defined as the inlets. The red faces were defined as the outlet, and the airfoil was defined as a wall. The 4 other sides of the rectangular domain not shown were also set to walls. The inlets were set as a velocity inlet and initialized to have a magnitude of 50 meters per second. The components of the inlet velocity varied for the 4 angles of attack of 0, 5, 10, and 15 degrees. The outlet was set as a pressure outlet with a gauge pressure of 0 Pascal. Once the flow was initialized from the inlet, the solution could be calculated. The pressure contours generated after a solution was achieved met expectations. There was a lower pressure exerted on the upper surface compared to the pressure exerted on the lower surface. This was the case for all 4 angles of attack. As the angle of attack increased, the pressure also increased. This once again met expectations, as it is known that up to stall, increasing angle of attack increases the lift generated. The interesting results come from a visualization of the velocity path lines. At an angle of attack of 0 degrees, both wings generate vortices at what would be the inboard portion of the modeled wing. However, it is at the wingtip that a difference is present. A small vortex is present in the wing without the winglet, while the wing with the winglet does not have vortex formation. As the angle of attack increases, so does the size of the vortex on the wing without the winglet. At an angle of attack of 5 degrees, the winglet begins to show a small curvature in the path lines indicating the onset of a vortex. At 10 degrees, flow separation begins to occur at the middle of the wing, while the vortex forming off of the winglet only grows a small amount. At 15 degrees, the flow over the wing becomes very separated and turbulent. The flow also begins to separate from the wing with the winglet, but to a lesser degree. The vortex forming off of the winglet once again grew a relatively small amount. To conclude, it is safe to say that winglets can help reduce wingtip vortices. The results provided showed a distinct difference in vortex size between a wing with and without a winglet. Further analysis could be continued by looking at different winglet designs to see if even more advances can be made.